Do you agree? I'm about to do that. Hey, can I point something out before I do that? When you're looking at this vector equation of this line, right here, the 4 in front of the t and the 8 in front of the t, that 4, 8, wasn't that the direction vector? Wasn't that v? Wasn't v 4, 8? Was it? Yes? Keep that in mind. 4, 8. You can see it in this equation. You can see the vector. You can see it in here too, 4 and 8. Let's look at the symmetric equations. We're going to see if we can find that again, that 4, 8 in there somewhere. So to find symmetric equations, take each of your parametric equations and solve for t. So I'm going to take the first equation. I'm going to subtract 3 and then divide by 4. That's t, right? Subtract 3, divide by 4. This one, subtract 6, divide by 8. So y minus 6 over 8 equals t. You understand what I'm doing there? Now set them equal to each other. So if I set them equal to each other, I get x minus 3 over 4 equals y minus 6 over 8. This would be our symmetric equations. Anybody notice anything about those symmetric equations with that 4, 8? Or is the 4, 8 just like glaring? Well, they're in the denominator, right? What I'm getting at is if somebody gives you the symmetric equations, so someone says, hey, here's a symmetric equation of a line, the symmetric equations of a line, you can already tell me what a direction vector is, can't you? The 4, 8 is just going to be the two bottom numbers. Okay, we're going to do this. Actually, you're going to do this. What's the difference between this problem and the previous one? Three-dimensional. So you're going to actually come up with the vector equations, the vector equation of a line in three-dimensional space. So see how you do. I'm going to give you a few minutes to work on this. Does anybody have any questions? Did anybody do it different? Did anyone pick a different R naught? Like, did anyone pick this one for R naught? No? Everyone did that? Pardon?
How did you get C?
How'd I get C? I'll explain that in a second. Let's get to it first. Make sure everyone's clear on all of this. Sure nobody has any questions? So R naught, any vector that goes from the origin to any of those points, either one. I picked this one. And then I chose my v vector to be the vector between these 2 points. So I did a subtraction, this minus this, created my direction vector, right? Is that a question? No? So remember, this right here is the direction vector. That's going to be an important thing later when I'm saying, hey, you need the direction vector. Hey, what's the direction vector? That's what I'm talking about. Because really, think about in algebra, what were the two things you needed to find to draw a line in college algebra or whatever? What were 2 things to draw a line? 2 points or a point and a slope, right? You could either have 2 points or a point and a slope. This is kind of like, hey, we need the point and the slope. The point is where am I? And then this is like, where am I pointing? Like, what's the direction? What's the slope? It's not the same because it's not necessarily on a flat sheet of paper anymore, but same concept. All right, so we plugged into the formula, and that means R naught plus TV. R naught plus TV is the formula. R naught plus TV, right? And then plugged in, cleaned it up, and got this. Now, our parametric is just x, y, z, so just write the equations. And then solve this for t. So move 3 over, divide by 4. If that's t, and then solve this for t, they're the same, right? Subtract 6, divide by 8. Here, add 4, divide by -3. All of those are equal to t, so they're equal to each other. Is that,
Yeah.
we're good now? Okay. That's it. Also notice, direction vector, 4, 8, -3 is here. Questions?
D?
Oh, D. Find, oh good, I'm glad you pointed that out. Find where this line intersects the YZ plane.
Do you let x equal 0?
X is 0, yeah, so if you're in the YZ plane, you're going to let x equal 0, right? So where should I do that?
The parameter?
I can do that in any one of these, right? But the one that makes most sense probably in the parametric. If you're going to intersect the YZ plane, so this will be part D. YZ plane means x is 0, right? And if x is 0, using this, you get 0 equals 3 plus 4t, and that tells you that t must be what? -3/4. And if t is -3/4, right? That's what it's going to require. T has to be -3/4 for this to happen. Then you can go back to these 2 equations and get your y and your z, right? Or you could just come back to the very beginning here and plug -3/4 into -3/4 into this. Either way, what should happen if I plug -4 in right here? 0, right? Because that's where we got it from. And then these 2 are going to spit something out. So let's go ahead and get what they spit out. I'm just going to do it that way. What's r of -3/4? So this is going to be a vector, right? Which is 3 plus 4 times -3/4. And then we have 6 plus 8 times -3/4. And then -4 minus 3 times -3/4. 0. Here is 2, 0 again. Just coincidence, all right? And then this one, negative what? -7/4. -7/4. So that point's on the z-axis. That's a vector, but we can look at it as a point, right? Where does it intersect the plane? We would say at 0, 0, -7/4. At that point. Is that clear? All right, let's move on. All right, determine that these lines are skew. So I give you some lines here, and I want us to determine that they're skew lines. And what does it mean to be skew? We need to know that before we can show that two lines are skew. We have to know what that means. Would you mind hitting the light switch to the far right? Yep, thank you. Determine that these lines are skew. That is, they do not intersect, and they are not parallel, and they are not orthogonal. Now, let's first understand what this notation means. L1 means line 1. Colon. I give you the vector form of the line. So I've given you the x, y, and the z. Now, what is the parameter that we're using to draw that line? What's the parameter? T. T is our parameter, right? Now, we have a second line. The second line, and it again is given in x, y, z, right? These are parametric form. This, if we set that equal to x, y, and z, those would be our parametric equations. But what's the parameter for that line? S. Could I have used t? I could. T is a dummy variable here, okay? T is a dummy variable. The reason why I did not use t is the following. If I draw, let's say I draw this line, right? I draw this line, then I'm going to use different values of t to get points on that line, right? And maybe maybe t equals 1 gives me this point right here. Then I have a different line over here, right? And I draw all the points on this line, and let's say I'm using t also. It's going to give me maybe t equals 1 over here, maybe gives me this line. This line and this one, the two that are here, the t's are not connected to each other. In other words, what t does to this line, t doesn't do the same thing here. I'm trying to think. Let's think about it another way that maybe will be less confusing. If I'm trying to figure out if two lines hit each other, right? Right? Then I'm trying to figure out, is there a t that I can plug into this line that would give me a point that also lives on this line, right? And let's say I find a t here. That t, I don't want it to necessarily have to match up with the t on this line, because maybe t equals 1. Maybe t equals 1. This is always so difficult to explain. Maybe t equals 1 gives me that point right there, okay? And it does hit this line at t equals 1. This is a catastrophe up here right now. Okay, t equals 1 gives me this line, this point on this line. But what if t equals 1 gives me this point on this line? And t equals 2 gives me the point where they intersect on this line. The t's aren't married to each other here. All the t's draw this line, other t's draw this line. So we use a different parameter so that we can possibly find that intersection point. If you use t for both, you're going to be in some trouble trying to find a solution. So that's why there's different parameters. All right. With all that said, let me go through these. First of all, are they orthogonal?
So can we just use the direction vector of that?
Okay, can we?
Because it's like a segment of the line, so if we just compare the direction vectors, then we can compare the two lines.
Yeah, exactly. Perfect. So if we have two lines, if they're orthogonal, right, they have to be like this. We know for each of these lines we have a direction, right? Both lines have direction vectors. So imagine a vector on this line and a vector on this line. The direction vectors, if they're orthogonal, right, then the direction vectors should, how do we check orthogonality? We dot product the vectors, right? So what is the direction vector of this line? Direction vector is what? 1, 3, -1. So you're just basically pulling the coefficients off the t's, right? That's all you're doing. There's a 1 here, a 3 here, and a -1 here. So the coefficient on the t's gives you the direction vector. What's the direction vector of this line? 1, 1, 1?
2.
1, 1, whoa. 2, 2, 1, 4. Okay. 2, 1, 4. So coefficient of the variable, coefficient of the variable, coefficient of the variable. Those are our directions. Now let's dot them. Okay? So let's dot these. What's 1, 3, negative 1 dotted with 2, 1, 4? It's not 0, right? Not 0? And we need 0 for orthogonality, don't we? Is it 0? 2, 3, negative 4. It doesn't add up to be 0. So are they orthogonal? No. Okay. These lines are not orthogonal. And this is pretty cool. We have 2 lines in 3-dimensional space, and within like a minute, we were able to determine that they're not orthogonal to each other. That's pretty cool that we could do that so quickly. Now, are they parallel?
Cross product.
We could cross product and check for 0, but do you remember me saying I don't like doing that because it's harder?
Yeah, they have to be multiple.
Multiple scale.
Are these scalar multiples of one another? No. So notice 1, 3, negative 1, not scalar multiple of 2, 1, 4. Therefore, y'all seen these 3 dots with a triangle before? That's shorthand mathematical notation for the word therefore. Therefore, what? Not parallel. It's just because we're lazy, we don't like to write the long words in math, okay? Therefore, it's not like supposed to be like, let's just come up with some cool symbol. It's just, we're just lazy. All right, therefore, not parallel. All right, one more thing to check. Do they intersect? This is a harder thing to check.
Can we equal the components?
Yes, exactly. If these 2 lines hit, right? If they hit each other, then there has to be an x, y, and z that live on both lines, right? The same x lives on both lines, the same y is on both lines, the same z. So what we're going to do is we're going to equate the x components, the y components, and the z components. So I'm going to write 1 plus t is 2s. I'm going to write negative 2 plus 3t equals 3 plus s. And finally, 4 minus t equals negative 3 plus 4s. And this right here, I have just created a system of equations. I have how many equations?
3.
How many unknowns?
2.
2. So if there is a solution, I should be able to find it. I have more equations than unknowns. It's bad when you have it the other way around. When you have more unknowns than you do equations, then you're going to have trouble nailing down a solution. All right, so any suggestions on how to go about this?
Solve the first 2 and then check the x and
Yeah, let's just treat it like, let's just look at those 2 by themselves first. You can solve that system, right? Let's just solve this little 2 by 2. So we have different methods for this: elimination, substitution. It's really kind of your call. I think for me, I like the idea of just solving this for t. Is that okay with you?
Yeah.
Solve that for t. If I solve that for t, I get 2s minus 1. I'm using substitution, which I prefer elimination, but substitution just seems to lend itself well to this problem. Once I substitute this, t is 2s minus 1, I'm going to take that and plug it into the second equation, right? So negative 2 plus 3, 2s minus 1 equals 3 plus s. You'll see what I've done? Replace t in the second equation with that. And now I have a single equation, one variable, right? Let's try and solve for s. Negative 2 plus 6s minus 3 equals 3 plus s. 5s on the left side. On the right side, 8. So s must be 8/5. Okay? So what? S is 8/5, big deal. What now? Let's figure out what t is, right? So let's figure out what t is. To get t, go back to this equation. So 11/5. So what? S and t of that. Now what? Yeah, don't forget this part. This is the most critical part. We know that we have found a t and an s that make these two true, right? The question is, does that t and that s make this true? If it makes this true, then we have found that they do intersect somewhere. But it's got to satisfy all three equations at the same time. So let's try it in here. Do you understand what I'm saying? We have found an s and a t that are making the first two conditions hold, which means that was our x coordinates and y coordinates, right? So we found an s and t where our x and y coordinates match. The question is, does the z coordinate match? And let me try it. 4 minus t was 11/5 equals -3 plus 4 times 8/5. Is that a true equation or not?
No.
It's not true? They're not equal? So? They don't hit. What if this would have been true? What if this would have checked off? They intersect then, right? They intersect. But since it does not equate, they do not intersect, and that's the definition of skew. Skew means not parallel, not orthogonal, and they don't hit each other. They're skew. We good? Questions? Does it feel like Monday?
Yeah.
It does. We're going to talk about planes now. We have 15 minutes. I know I'm ready to go too, but you waited all weekend, so you may as well stay for a little bit. Planes. This section is about lines and planes. Does anybody know the equation of a plane? Like I start off when I started talking about lines, right? And I said y equals mx plus b. And I said that's the standard equation for a line. We're going to kind of erase that from our minds right now. And we're going to define a new thing called the vector equation of a line. And this is what we're kind of walking away with. Hey, where were line segments? Did I jump? I missed that. Hold on. I think I jumped too fast. Ooh, somehow I jumped over that. I need to talk about this. Sorry. Line segment. Oops. Good. This'll work out better. All right. The difference between a line and a line segment is, the line goes in both directions forever. Line segment. Sometimes we only want to be able to draw just a piece of a line. So if you're given 2 points, all right. If you're given 2 points, let's say points, not vectors, x naught, y naught, and x1, y1, and you want to draw the line segment, okay? And we can even draw a little bit of a direction on this. Like if you want to start drawing this segment, starting here and moving across to get to this point, the way you do it is exactly the same as what you did before. Setting up the vector equation, we're still going to do this. R of t equals r naught plus tv, where v is still the direction vector here. But all we have to do to draw this segment is restrict our t. We're going to actually put a domain restriction on our t. We're going to say you're not allowed to use all t's anymore. Just t inside the interval 0, 1. T is an element of the interval 0, 1. So let's just think about this. What would happen if t was 0? If t was 0, that would be gone, right? And all you'd have is r naught, which should draw me that first point, right? What if I do 1? Then it's going to be r naught plus tv. So it'll be, here's the origin. It'll be r naught gets me to here, right? And then add v, I should be here now, right? All the way at the end. So this gives me my left endpoint. This gives me my right endpoint. So now let's plug in something in between, like 1/2. If I do half of v, won't that be r naught and then half of the distance? Right? So imagine every number between 0 and 1 just gives you some factor of how far to travel across until you get to the end, which is 1. The important aspect of this formula is that this formula will only work if your r naught came from the starting point. If you use your ending point, it's not going to work. And your v also must go from endpoint. You know how we get v, we subtract, we go this one minus this one? You have to do that order. The endpoint minus the starting point. Now the book does something slightly different, which I don't really care for. So I'm not going to, that's what the notes say. But for us, just do it the way I've shown you. Go 0 to 1 on your interval. Planes. Back to what I was saying now. So I said for lines, you had y equals mx plus b, and I showed you a vector equation for a line. What about a plane? Do you remember the equation of a plane in algebra? ax plus by equals d. That sounds very familiar. ax plus by plus cz equals d. Or something like 3x minus 4y plus z equals 7. That is correct. That is the equation of a plane from college algebra. Now, you may not remember them as like this. What you might remember is solving systems of equations when you had like 3 equations and 3 unknowns. And then they told you, hey, wait a minute. Geometrically, this is the intersection of 3 planes. You may not have spent a lot of time actually talking about the fact that the general equation for a plane is that. Right? But that's what it is. All right? So this is what we've worked with in the past. But I know not really. We haven't worked with it a lot. Just a little bit. Not as much as you worked with this, right? For sure. Well, I have good news and bad news. The good news is that we are going to work with this. This is what we're going to work with. So you get more practice. If you haven't seen enough of this, good, you're going to see plenty of it. And the bad news is that we're not going to do a vector equation for a plane yet. It'll come. It'll come in chapter 12. We will actually have a vector equation for a plane. But here, just like we went from line to vector equation of line, we're not going to do plane and then vector equation of plane today. So hang tight. Chapter 12, we'll see that. That's pretty much what I've said here, that we're not going to do a vector equation. How many points do you need to define a line? You told me this a second ago?
2.
2. How many points do we need to define a plane? 3. So once you have 3 points, as long as they're not on top of each other, the same point, 3 distinct points, then you have defined a plane. And here is a picture. There. So once you have 3 points, there's no way to get around it. You have defined a plane, right? And we've done some things with this already, right? We've come up with some vectors already in the past, and we've crossed them. What were we doing that for? When we had 3 points and we were crossing vectors, what were we doing?
Figure out a vector perpendicular.
Yeah, we were trying to find a vector perpendicular, right? That was We use that to find the area of a triangle, right? Do the cross product and then area. Okay. Very good. So let's go back and just look at this for a second. We've got 3 points, right, living in arbitrary space. Let's just see what would happen if I did this. Why don't I just draw 3 vectors that all start at the origin and go out to my points, all right? Start with that. I could do that, right? All I've done is turn my points to vectors. Now, let's just pick 1 point to start with and draw vectors going out in each direction, right? Like from that point to the other 2 points. And let me take the other 2 out of here, or the other 3 vectors out. So now I've got those 2 vectors, and they live on my plane, right? If I cross those 2 vectors, I'm going to get that vector, right? And that vector is orthogonal to the plane. Doesn't look like it. I think that's just some problems with my scaling on my rendering of this. That should be orthogonal. That doesn't look orthogonal, does it? There we go. That's a little better. It's just perspective here. There we go. There. That's a little better, right? That look orthogonal to you? That vector right there is a very special vector. We call that the normal vector of the plane. Every plane has a normal vector. And that normal vector, the property that makes it a normal vector is the fact that it is orthogonal to the plane. So if you have a flat sheet of paper, right? May I? Okay. This is a normal vector, okay? That's a normal vector. Any vector that is orthogonal to the plane. It can be longer, shorter. It just has to be orthogonal to the plane. We will be interested later in finding normal vectors for planes. Everyone understand geometrically, though, what it is? All right, so it turns out that in order to define a plane, if you want to define a plane, we already said you need 3 points, right? That's fine. But you can have less information than that. All you need is 2 things. A point on the plane and the normal vector. A normal vector. Any normal vector. And why is that? And let's think about this. Can I borrow this again? Okay. I'm going to grab it in a second. Let's say I have a point in space, right? That doesn't define a plane. But now I give you a vector. Does that define a plane? Yes. If I tell you that that vector is a normal vector, there's only one plane that I actually can put in here that's going to cross through that point and be orthogonal to that line. There's no other plane. I can't do this. It's not orthogonal, right? No other pitch I can put to this. There's this vector uniquely defines almost like a direction of my plane. So that's all you need to define a plane. Give me a point on the plane and any normal vector to the plane, and we are in business. In that case, x naught, y naught, z naught, that is the point. And then the normal vector, which we use the n there, is called the vector ABC. That is almost like the direction vector of the line. That's the normal vector of the plane. When you have that, once you have those 2 pieces of information, we have this very, very important formula, which I made too big. Did I go too far? Here we go. This is it. This is the equation of a plane. Remember, ABC was the normal vector. So you put A, B, C, and then you, in parentheses, x minus x naught, y minus y naught, z minus z naught. And then what you would just do is distribute. If you distribute this through, the A and the B and the C, do you agree that AX would stay AX? And AX naught, since x naught is a number, AX naught would be a number, B times y naught would be a number, C times z naught would be a number, and you could put all those numbers together and you would get the A, X, B, Y, C, Z, and then all those numbers put together would just call D. So you get all of this equals 0. And that's the equation of a plane. So you may not have realized this when you were studying linear or equations of planes, but if we take something like this, minus 4y plus z equals 8, okay, there's the equation of a plane, right? You may not have understood this when you studied them, but if you look at this vector, 3, negative 4, 1, okay, so I'm pulling off the coefficients on the x, y, and z respectively. That vector pointing out in space, wherever that is, that vector is perpendicular to my plane. It is orthogonal. Now, what I don't have right now, this is the normal vector. What I don't have is a point on that plane. Could you get me a point? Could somebody give me a point on that plane? Did I hear 0, 0? No. Would 0, 0, 8 be on that plane? Would that point be on this plane? If I plug in 0 for x, 0 for y, and 8 for z, would this be true? Yes. That point lives on that plane. All I'm wanting you to see right now is that if someone gives you the equation of a plane, you can pop the normal vector off that equation just by looking at it. Just by looking at the equation, you can identify the normal vector. All right, we're out of time. We will pick up here talking more about planes. You should be able to handle on the take-home exam all the way up through number 5 now.